Welcome to the Anamena video tutorial about concentrating solar power. This lecture is the Unit 1, Block 07, Water Treatment. My name is Christian Sattler. I'm head of the Department of Solar Chemical Engineering at DLR's Institute of Solar Research. I have 15 years of experience as head of several units at DLR for solar chemistry, solar fuels, especially hydrogen, and solar water treatment. And this will be the topic here. Solar water treatment is a little bit out of the scope of these tutorials because although it is possible to use CSP installations, normally it is done by non-concentrating solar reactors. But as water is not available in small quantities but in large quantities, the installations are large and somewhat related to CSP plants. There are 10,000 of research papers on water treatment processes published already, and there are two main classes of reactions that are under research, and both belong to the so-called advanced oxidation processes, or AOPs. These are heterogeneous photocatalysis, where we use semiconductors as catalysts, like titanium dioxide, and homogeneous photocatalysis, where you use dissolved ionic photocatalysts, like the Fenton reaction. Most degradation of nearly all components known as contaminants are carried out. There are worldwide activities on these, and worldwide excellent work is carried out. However, the development of the plants is rather limited, and there are two main groups working on it in Spain and Germany. The problem of solar water treatment is that for all these photochemical effects, we only can use the energy-rich part of the solar spectrum. So classical photocatalysts only use the UVA part of the light. And the development of these catalysts must be that we can use even a wider part of the solar spectrum, up to 400 or maybe even above 500 nanometers, so that the efficiency of the processes improve. The principle of the semiconductor photocatalysis is rather simple. You just put the material, which is a solid, into your water that you would like to treat at sunlight, and with the UV part of the sunlight there are electrons and electron holes formed on the surface of this photocatalyst, and these electron hole pairs react as well as reducing as oxidizing agents by activating oxygen or hydrogen peroxide, and with these very active substances they can degrade nearly all organics and can change oxidation stages of inorganic ions. This is especially important as, for example, some heavy metals or with arsenic. Some of the higher oxidized species are, for example, more toxic than others. The light-enhanced Fenton reaction works differently. Here you have dissolved iron ions in the water. You need to run them at a rather narrow pH rate between 2.8 and 3.2. And you have to add hydrogen peroxide as an oxidizing agent. However, with iron complexes, you can use sunlight up to 580 nanometers, so a much wider part of the spectrum can be used in these reactions. There is also another benefit. The catalyst can be separated much more easily from your treated water than the titanium dioxide, as the filtration is not as critical, and the recycling of the catalyst is very simple, as it can be dissolved in acid and then it can be produced newly for the same reaction as before. With the titanium dioxide, sometimes there is a poisoning of the catalyst by contaminants like chlorine or like some heavy metals that reduce the catalytic activity. To operate such water treatment, reactors are very important, and our main focus was in the development of such technologies. As you can see, we started from laboratory reactors in the mid-1990s, very small reactors where less than a liter could be treated. And our idea was to use the knowledge that we have from CSP to set up larger plants that can be operated like a CSP plant. We did this together with a lot of partners all over Europe and even beyond that. And so the first major applications of the technology were done by Spanish companies, for example, Hidrocen close to Madrid or Albaida close to Almeria. As you see here on the two top right pictures, even on 1999, a plant with a surface area of more than 100 square meters was set up, and this plant is still in operation. It is close to Madrid in Arganda del Rey, and we are very proud that we could show that even after more than 10 years this plant operates well. But it is one thing to develop the technology. The next thing is you must bring the technology into the places where they should be used best. And so education and science are important. Two examples are shown here. A development done at the University of Uberlândia in Brazil and a school lab at DLR where we developed the technology and we brought it to the scientists, but also to pupils and students to know about the technology and know what can be done. And the next step is then to produce a reactor that is simple, cost efficient, and also chemically efficient. And as an example for how to treat solar water in large scale, I would like to tell you now how we did the development of such reactors. Of course, we also started in the laboratory with small reactors where we just want to find out how reactions work. And I have here as an example hydrazine, which is used, for example, as a rocket engine, which shall be treated via photophantom and UVA light as we have it in sunlight. You see, the small installation is good for batches of 4 to 5 liters, and the power that we use is about 9 watts, so very little power. But even with these very small installations, you see that we achieve a very good degradation after very reasonable times between some minutes and 2 hours. We then scaled up this to our solar receivers, and we started to think about how must such a receiver look like. And it was important that the receiver modules can be handled easily, they must be rigid, they must withstand long times. As I told you, the plant in Madrid is already working for more than 10 years. So we designed these receiver modules out of glass tubes, and we added very efficient fluid distributors and fluid collectors to it so that we could guarantee a homogeneous flow through all the plant. We needed a simple but efficient stand, which we took from PV. So here is the connection to existing technology. And then we tested it in a small prototype plant in our test center in Cologne with an aperture of 7 square meters and a volume of 140 liters. And it was operated very successfully. The next step was to go to where the wastewater is really produced. And this is the DLR test facility in Lampertshausen in southern Germany, where we have some cooling waters which is contaminated with such hydrazines. And as you can see, we developed not only the plant in a way that we just put more modules together, but we changed the module style. As we learned from our first module, we changed it in a way that the glass tubes became longer, and we set up a plant about 5 times the size that we had in Cologne, in Lampertshausen, and operated it there in parallel to the existing water treatment plant on site. And we could show that we could reduce the cost of the water treatment drastically with this technology. So we also thought about how to scale it up to a size that we could treat the whole water amount of this facility of DLR, and we set up a receiver with 240 square meters of aperture, which has batches of 4.5 cubic meters, and with this plant we can treat the whole water of the site. So the plant is in operation since 2008 and now is operating permanently and shows excellent results. The existing conventional plant is only used as a backup there. So the technology is ready for the market, and the technology can be used in nearly every place where such wastewaters are available. We done also treatment of a lot of other contaminants, and we can design this technology to be adapted to all water problems. And here is the proof that this works as well in the field with our demonstration plant as in the laboratory. We could show that after 120 minutes, we could reduce the amount of hydrazine in the wastewater to 0, even when we have changing solar conditions. So you don't need the laboratory conditions to do this. We could also show that you don't need the direct radiation, but also with diffuse radiation, the reaction works as you don't concentrate the radiation. However, it is faster when you have more light getting on the tubes of your reactor. In summary, the scientific developments that are going on everywhere is to explain the degradation mechanisms of these reactions, what is really taking place in the chemical reactions, to develop more efficient catalysts, and to show that even more contaminant classes are degradable by these technologies, so that a broader availability can be shown. In the technological development, the receiver design is crucial, the scale-up and the demonstration, so that the society gets aware of the technology and more of such plants are used, especially for industrial application. And the present state of the technology is, it is ready, you can buy it, and you should use it as it can save you a lot of cost compared to conventional technologies. And I hope that there will be even more developments and more applications very soon. This is the end of this tutorial. Thank you very much for your attention.